Hi everyone, we're Team 23. We'll be presenting our analysis and redesign of an electric folding longboard. The highlights of our selected longboard design are that it has a central folding joint to reduce size for transport and storage. It also has a carrying handle that deploys in the folded state. On top of that, it also has a propulsion system that improves the riding speed of the board. We have identified two target markets, urban commuters and college students, as well as tech enthusiasts. While urban commuters benefit from easy deployability, high travel speed, and not needing to lock up the board, tech enthusiasts may be interested in flashier design considerations, like dual-wheel drive and music playing capabilities. These different profiles drove our variant differences. This is an exploded view of our CAD model, and shown here is our FAST diagram. We have one main functive relating to transporting the skater using the board. In our function component mapping matrix, you can see that each component is mapped to at least one function, and some, like the bearings, share the same functions, giving us opportunity for consolidation and improvement. Our primary and secondary customers have different goals. Namely, tech enthusiasts may be interested in more advanced technology. Some components that have more opportunity to be integrated with those high-tech components are the motor and drive unit, as well as the battery compartment. Therefore, these components were selected to be our modules. Showing the differences for our modules, the battery component variant includes a material change, added speakers, and reduced size, while the drive unit variant is upgraded with all-wheel drive. Shown here are the exploded module variants, and shown here are the common interfaces for our battery module variants. Here is the product family assembly design. In our redesign of our PFAD, we achieved efficiency gains by delaying differentiation of the large pulley and all-wheel drive.
Next is design for manual assembly. For a manual DFA, the first step we took to identify parts was to figure out the assembly time for each. With this, we could tell that the fasteners were the overwhelming majority of time spent assembling, so we chose parts that had many fastener interfaces, namely the decks for our platform and battery compartment for the module. The quad chart tells us that these parts are high importance, so time is well spent to focus there. As you can see, the decks have 34 holes for fasteners and no locating features. With changes to the base plates and a part consolidation to remove fasteners and adding a few locating features, we were able to bring the bolt count on the decks down to 20. Initially, the connectors and battery compartment used 8 total fasteners to attach to the deck. For this redesign, we were able to both reduce the fasteners from 8 to 2 and consolidate the parts. Additionally, the inside of the battery compartment has locating features to put in the batteries. To summarize all of the parts changed for manual DFA, we are able to save about 147 seconds, with the majority being from deck changes and a 1.66% increase in efficiency. Although all the fasteners were accounted for under deck changes, some of these did double benefit for the battery compartment.
Now for design for automated assembly. We selected the axle subassembly containing components of the axle, wheel bearings, wheels, washers, and the securing nut. From the function component mapping matrix, these components share the system functions of absorb force and control direction, which indicates a strong opportunity for part consolidation. The before design contained 4 wheel bearings per axle, and the wheels were not symmetric. Additionally, the team opted for a snap ring instead of a nut, with the wheel bearings pressed into the wheels to eliminate washers. These changes helped us achieve DFA objectives of reduced part count, reduced part variety, and increased symmetry. There are no expected changes to product function and manufacturing costs, and overall observed an assembly cost reduction of $1.40. The original automated assembly cost analysis containing an axle, 4 washers, 4 bearings, 2 wheels, and 2 nuts gave a total assembly cost of $5.09. With the modified design for automated assembly, this total cost was reduced to $3.57 by having 1 axle, 2 symmetric wheels, 2 wheel bearings, and 2 snap rings.
The first process for process selection was the deck. Here you can see the CAD with dimensions, some of the critical dimensions to support the structure of the board are thickness of the deck as well as the holes. And for both of these, 0.1 millimeter tolerance is deemed appropriate, primarily due to the shape, tolerances, and batch size. Machining was deemed to be the preferred process. It would be milled with some rough and finishing passes and then drilled for the holes. The other part assessed was the battery compartment, critical dimensions being the wall thickness to enclose the batteries, as well as hole diameters to ensure that this can be mounted appropriately to the other parts of the board. And for this one, primarily due to the shape and material, injection molding was deemed the preferred process. There would be some additional manual cleanup required at the end to support final assembly. The first part assessed for design for manufacturing was the battery compartment. Running DfM Pro, recommendations included adjusting the interior rib, adding a draft angle, and having uniform wall thickness, and reducing mold wall thickness. So some of the changes that we did in the design for manufacturing enhancements were adding an interior draft angle, reducing the thickness of attachments, which was the maximum wall thickness, and then changing rib orientation. And what we saw was a cost reduction of about 50% due primarily to the reduction in maximum part thickness, which was the major driver of cost, dropping it from about $6 to under $3. There was no product function or assembly cost impacts.
Pro on the deck was conducted, and it showed issues with deep radius corners, narrow regions and pockets, and sharp internal corners. Design for manufacturing the deck, we decided that we would remove the insignia feature, radius to sharp corners, and shorten the board by 25 millimeters. DfM cost estimation showed that the cost went from $20.02 to $18.67, with the main driver being the setup cost for the insignia feature. The secondary one would be the smaller deck, which was the material cost and machining cost. There is no impact on production function nor assembly cost. As far as a price quote comparison between hubs and the analytical method showed the analytical method is 2 times the hubs cost estimation, probably due to the extrapolation and some assumptions, but is in line with the 7 to 10% cost reduction designed for manufacturing.
Along with the product, we plan to offer services to improve the customer experience and expand public infrastructure. To improve the customer experience, we'll offer board maintenance to provide tech refinishing and wheel and bearing replacement services. With infrastructure demand for mobility solutions, we plan to expand this infrastructure by providing shared mobility services to create a network for reliable access to publicly shared boards. To make this a success, complimentary charging will ensure these boards are ready to use when picked up. And lastly, public infrastructure is improved by establishing a recycling plan to dispose of used batteries. To conclude, design for manual assembly resulted in a 10.9-second time savings from battery compartment changes and a 136.84-second time savings from deck changes. Design for automated assembly resulted in a $1.40 reduction in cost by simplifying the axle subassembly. Design for manufacturing helped the team achieve a $3.26 reduction in cost for the battery compartment and a $1.35 reduction in cost for the deck. Offering a critique, the team could have made more improvements to the chosen parts to reduce manufacturing time even more. Next time, we'd like to strive to reduce more fasteners and design for assembly and explore topology optimization of the base plates for design for manufacturing.